Hello students. So today we are going to see the next topic, which is moment of momentum. Moment of momentum, which is also known as angular momentum, which is denoted by the symbol L vector. L vector. It's a vector quantity. Okay. So first thing that we should note here is the definition, mathematical definition again, L vector. L vector is defined as R cross P. Now again, exactly this topic is going to be exactly like the moment of force or torque. Okay, so suppose about this point O you want to calculate. This is R vector. Body is at this point A and it is having an angular momentum, linear momentum P vector. Of course, you know linear momentum is mass into velocity vector, right? So what is angular momentum L vector about that means about a point you are calculating. The body is right now at position A. So this is the definition, R cross P, right? And if you take the magnitude, it will be RP sine theta. Again, this can be written as R into P perpendicular, or you may write this as R perpendicular into P. Remember what is R perpendicular. So you can split or resolve it according to your convenience of given the question. So suppose this is R vector, this is P vector, right? And let's see the angle between them is theta. So if I resolve P in this direction, that is P parallel perpendicular to R, this is P perpendicular. Okay, so when you write this R into P perpendicular, so you can use this R into P perpendicular. So P perpendicular is nothing but P sine theta. And how do you draw P perpendicular? You need to resolve P parallel and perpendicular. P it is the P which we are resolving. R we are not resolving. If you are resolving R, then you will write angular momentum as R perpendicular into P. Then in this case, you are going to resolve R. Okay. So let's resolve R, and if this is angle theta, R can be resolved parallel to P and perpendicular to P. So R perpendicular is R sine theta. So depending on the question or given condition, we can resolve any one of them and you can calculate exactly similar to torque. Okay. So here also you can see some case studies. I think the same type of case studies that we discussed in the talk. First case study, if you take the projectile motion, consider the projectile motion. Body is projected with the velocity u, and this is the angle theta, and this will be the projectile motion, right? So let us say when the body is here at this topmost point A, or it is at the bottommost point B, this is O. So what is angular momentum at A about O? Similarly, what is angular momentum at B about O? Okay, so these two calculations you can understand. If you consider angular momentum, now again angular momentum means vector we have to draw, momentum we have to draw. So when the body is at the topmost point, momentum is only in this direction. Momentum is mass into velocity. Velocity is only u cos theta. Okay, that's the only momentum here. Now R vector means you have to join this, right? You need to join this. This is what is R. So what you can do is you can try to extend this or draw the line of motion. Line of motion is horizontal here. You can see this mu cos theta. This is going to be horizontal. This is called line of motion. Line of motion. So from this point you drop a perpendicular here to this. That is what is R perpendicular. And obviously you can see R perpendicular is nothing but the H max, right? The maximum height, H max, which is nothing but u square sine square theta by 2g. Okay, and now you want to calculate the angular momentum here. That R perpendicular into P you can do. R perpendicular is this u square sine square theta by 2g, and P is nothing but mu cos theta. So you can simplify, you can get the answer, right? You simplify this, mu cube, right, sine square theta and cos theta divided by 2g. Correct. This is the angular momentum. Similarly, in case of this second case, angular momentum about V you want. Now you see here the momentum will be m into u, because with the same speed it will be reaching the ground, right? And what is R here? R will be this one. This is R. Of course, R is capital R here, which is the range. Now here you can see that also to note that this angle will be same when it is hitting theta. So now this point, at this final point, what we need to note is which one should be resolved. Should we consider R perpendicular into P or P perpendicular into R, which is better? So you can clearly see that resolving momentum into perpendicular direction is mu sine theta. That is better, because then this distance R we can use as range, isn't it? So if you are using here this angular momentum, you can use this angular momentum, angular momentum at P as R into P perpendicular. So R is range, P perpendicular is mu sine theta. Range is u square sine 2 theta by g, and that is mu sine theta. This you can simplify and you will get angular momentum. Here is mu cube sine 2 theta into sine theta by g. Correct? So you can calculate angular momentum in this manner, right? I hope you have understood this angular momentum calculation about a point. About a point we are calculating angular momentum of the body, right? Okay, now another thing that we can now note is that angular momentum or torque, what we were calculating, it is about a point. But what about if they give about an axis? So calculation of torque, or you can say angular momentum, about an axis, because the calculations are similar, we are going to discuss this together. So let's take torque. So suppose this is a body, let us say this is a body, and there is an axis of rotation. This is an axis of rotation, and you have calculated torque of this body about a different point, right? You may have calculated torque about a point, but that torque need to be calculated along this axis, So when you are calculating torque about this, let us say you have calculated torque about a point somewhere on this axis, you can calculate. Let's say there is a point O on the axis, and you calculate torque about O. Torque about O. And let's say that this axis you can consider in this direction. There is a unit vector. First of all, we will define r cap. Let us say r cap is a unit vector, or r axis I will write. So here I am defining our axis cap is a unit vector along the axis. So torque about O is, let us say, tau. Okay, this is tau. Torque about O is tau. Now torque about axis. Torque about the axis can be calculated as, of course this is a vector, right? So this torque vector dot r about the axis we can take. Of course this will give us magnitude. If you want direction, you can still write this. Okay, it's like a component of a vector. As you calculate the torque, you can take component. Same manner, angular momentum will also be calculated about this axis. Okay, the same manner, angular momentum about the axis, the angular momentum can be written as L vector dot r about axis and r of the axis. Here what is L vector? Here L vector is angular momentum about O. Okay, it is angular momentum about. So we can resolve it just like a vector we are doing. That's the concept, the idea here. Okay, I hope you have understood this. Calculation we will be seeing it afterwards. Okay, this is the theory or the concept, right? So after this, now we can focus on studying the analogy between linear motion and angular motion, or you can say rotational motion. So let us write linear motion. Motion means here we can write both kinematics or dynamics. Rotational motion. So by using the concept of analogy, we can study all the things which are analogous. Okay? So first we can write mass. Mass is represented as m. In rotational physics, it is moment of inertia, which is written as I. Then linear displacement, let us say delta x. Here angular displacement delta theta. Similarly here linear velocity, which is v. Here angular velocity, which is omega. Omega is nothing but d theta by dt. Linear velocity is dx by dt. Right? So many analogy will come. Let us write more analogies. Let us add a lot of analogies in the list. Linear acceleration, you know that is a, which is dv by dt. Here angular acceleration, which is alpha, which is d omega by dt, right? D omega by dt. Then next, all these point by point analogy I am writing that you can understand. Then next you can take let us say force. Force is equal to mass into acceleration. Here torque is equal to I into alpha. This equation we are going to use a lot. Here this is Newton's second law. Remember, this force means it is the net force. Torque means this is the net torque. Net force is mass into acceleration. Net torque is I into alpha. Right? Then next, let us see some more analogy. Let us say angular linear momentum. P is mass into velocity. Here angular momentum is, instead of mass, I instead of V, omega. Okay. Then we can define, just like force is rate of change of linear momentum, dp by dt. Same manner, torque means again net torque only. Torque is rate of change of angular momentum. Right? Linear or translational equilibrium. What is translational equilibrium? Translational equilibrium means net force is equal to 0. Similarly, rotational equilibrium. Rotational equilibrium means net torque is equal to 0. Again, so this equilibrium gives rise to the conservation of momentum, theorem. Whenever the net force is 0, so the system momentum is constant. Correct? Similarly here, angular momentum will be constant. Okay? Of course, it's a vector. You may write it as a vector. This is the conservation of linear momentum. Conservation of linear momentum. This is conservation of angular momentum. Right? So many analogies, 8 analogies we have seen. Let's add some more analogies. Okay. 9th, how do you calculate work done? Work done is calculated as integration of force into displacement in general. Here also work done. This is work done by force. The work done by torque. Is integration of torque vector dot small angular displacement. Okay. Of course, if force is constant, you will take out, and then integration of dr will become delta r, right? So that you can do anyway, right? 10th, power delivered by a force is force dot velocity vector, and here power delivered by a torque. Power delivered by a torque is torque dot angular velocity. These are vectors, right? Dot product. That's why we have to use the vector products, dot products, and all that. Okay. Then one more thing that we can use is the work energy theorem. What is work energy theorem? Work done by the net force is change of kinetic energy. Work done by net force is change of kinetic energy. This is of course linear or translational kinetic energy. Work done by net force means net force dot displacement dot product. This will give change of kinetic energy means half m v square minus u square. Okay. Similarly here, how do we apply work energy theorem? Work energy theorem means work done by net torque. Net torque is change of kinetic energy, rotational kinetic energy. Okay, so what is rotational kinetic energy? That we can tell. So work done here is net torque dot displacement, angular displacement. This will give half I final omega 2 square minus omega 1 square. Okay, this is what it is. So many analogies will come, lot of applications are going to come. So we will be using all this in our calculations. I hope you have understood up to this. Further we'll carry on in the next class, right? Thank you for your attention.